All right, good evening. So let me remind you what we have done. Again, if you have any question, you can ask me at any time. I know it's tough, it's not an easy subject, so try to catch as much as possible. So yes, last week I had a small problem, and probably I still have a small problem, but I need to add in the set of Gaussian, I add the 0 random variable. So the random variable which takes the value 0 almost all the time, or all the time. You can think about it as the normal distribution with 0 mean, but also 0 variance. It's a definition, but it's useful because for the definition of Gaussian vector, x, it's a vector, it's a random vector, is Gaussian if whenever you take a scalar product with an element of Rn, now it's a distribution with value in R. Then if we say it's a Gaussian vector, if this random variable is Gaussian, and if in case this is 0, you need to have the 0 distribution inside the family of Gaussian random variable. So for consistency, I need to add this one. We also say that this vector, these n univariate random variables, so they have values in R, they are jointly Gaussian. So I introduced this notion of Gaussian vector. And there is a property which, or it's a proposition which says X is a Gaussian vector if and only if when you compute the expectation of e power ax, so this is a function of a random variable for all a in Rn, you have this formula where this is the expectation or the mean value of x, and so it's a vector. If x is a vector, this is a vector, and you do a scalar product with a. And this is a matrix applied to a vector multiplied by the transpose of a vector, so it is a number. By the way, no, it's okay. With this, you can see the importance of expectation and covariance, because if you know that you have a Gaussian random vector, they are uniquely defined by expectation and by covariance, so they completely define the Gaussian vector. Now, I also gave this definition of non-degenerate. If this is a matrix, a square matrix, so it's non-degenerate if the determinant is not 0. And there is a second characterization which says that it's non-degenerate if and only if whenever you write this equation, it's like in linear algebra, when you write this equation and obtain the 0 distribution, then, or 0 random variable, then it implies that A is the 0 vector. So it is a linear independence of the random variable. Think about a random variable is just a function. So if doing a linear combination of functions, you obtain 0, it means that these functions are not linearly independent. And finally, for family or for random vector, the joint probability distribution is, or for family which is non-degenerate, the joint probability distribution has this form where you have here's a covariance and here's a mean. Then I started introducing the next topic, which is a family of random variables. So from now, t is going to be the time belonging to this curly t. This curly t, think about it either as n, if you want to speak about discrete time, or as an interval, or as a half line from 0 to infinity. So it depends if you want discrete time or continuous time. So we are going to consider family of random variables. They are all from the set omega, our initial set, to capital lambda, which is part of a measurable set. And yeah, it's going to be a family of random variable. We say that this family provides a Gaussian process if whenever you fix n time, so in this set, you pick n times, so you have, for this, for this definition, I need to choose lambda is equal to r. Otherwise, it's not meaningful. For Gaussian process here, for the next line, lambda is just r. So we have family of random variables with value in r. We say it's a Gaussian process if whenever we pick n of them, it is a Gaussian vector in the sense given here. This is called a Gaussian process. So for any, this family of n times, and n is arbitrary, you have a Gaussian vector, so it's exactly in this framework. This is called a Gaussian process. And I gave you a few examples, and it's good to have these two things on the same blackboard. We have seen a family of Gaussian processes made of Gaussian vectors. The Gaussian vector is uniquely defined by expectation and covariance. That's why when I gave some examples last week, I just mentioned the expectation and the covariance, because if you know that it's a Gaussian process, this is the only information you need. And then I started, this is enough at a certain level, but sometimes we need some more information. So I started with a slightly technical notion. It's a filtration. So everywhere we have a F, which is a family of subset of omega. A filtration is a family of families of subset of F or of omega with a property that Fs is inside Ft whenever S is smaller than T. And everything is inside F. So these are sigma algebra. So it means they are stable for intersection, countable union, and countable intersection. And they satisfy this property. So it's you have more and more sets, think like this. And finally, I gave the definition of a stochastic process, and we are going to study it today. It's something rather complicated. You have first these three things is a probability space, so a set, a family of subset, and a measure on it, probability measure on it. You have one filtration, so a family of subalgebra, sigma algebra of this, indexed by the time, and you have a family of random variables from the set omega to a set lambda, which is not fixed here. It's written here. Each of them is from omega to lambda. The point and the tricky point is that they are Ft measurable. So I will recall, so this is the start of the new material. What means they are Ft measurable? So the first part of this lecture is rather tricky, but still you can enjoy it. I hope you can enjoy it. The second part is about Brownian motion. So let me just remind you what is this. Xt is Ft measurable. What does it mean? So let's say from omega to lambda, if whenever you take xt minus 1 of a, and now we should know what it is a set of omega in omega, which are sent by xt inside A. This is an element of Ft for any A in this. By the way, this is part of the measurable space here. This is a collection of subset of lambda. So think about this. Is it stronger to say that it is Ft measurable? This is a question. Is it stronger to say that it is Ft measurable, or simply that it is measurable with F? Which one do you think is stronger? Why with Ft? Right, this is a correct answer. Ft is smaller. So if you have to check that the preimage is in Ft, you have less freedom than if you are in F. So this condition to be Ft measurable is something stronger than just saying, oh, you are in a bigger set. So just an observation, yes. This measurability with respect to Ft is a stronger requirement. It's a stronger requirement compared to F measurable. So we assume something slightly stronger in the definition of a stochastic process. And by the way, we also say, this is another keyword, we say that this family xt, or t in this set of time, is adapted is adapted, yes, adapted to the filtration to FT. It's the same thing. I mean, it means exactly the other, that it is FT measurable, but it is just another keyword. So now we know what is a stochastic process. It's a rather complicated object, but we will see that it encodes many things. By the way, you will find, if you look at the literature, sometimes the definition is slightly simpler. They don't speak so much about filtration. For some process, you can forget the filtration. For some, it's important. So I decided to present the general framework. A remark. There is one filtration which is quite special. I'm going to I'm going to give a name. I'm going to give a name to this smallest sigma algebra. So sigma, you should not be scared by sigma algebra. It just means a set which is stable on the intersection, countable, complement, countable intersection, and countable union. That's it. So the smallest sigma algebra containing the set xs minus 1 of A for any A inside E. So you take all pre-image, you take intersection, you take complement, you take union, and this generates a sigma algebra. So this is a quite, if I give you this random variable xs, so xs is from omega to lambda, you take all subset in your measurable set lambda, and you take the pre-image. So this is the smallest sigma algebra. Okay. And now, if I do it, I would have a natural sigma subalgebra for each given t, but I don't have a filtration. I don't have this condition. I would have something for each s, but I wouldn't have some inclusion. There is no reason why I should have inclusion. So I construct, this is a curly G of t. It is still the smallest sigma algebra containing all sigma of xs for s more or equal to t. Okay, how you should think about this? I just want to satisfy this filtration. So you have a big set omega. In this, you have the blue sets. The blue sets, which are, let's say, element of sigma of xs for a given s. You have another one, family, which are the element of sigma of xt. But now, if I want to have a filtration, I need to construct something for I assume t is bigger than s, just for this picture. T or s smaller than t. If I want to respect the filtration, I need to define set g of t containing both x sigma of xs and sigma of xt. So I need to consider something which contains both. And then if I do it for all s smaller than t, then we end up with a filtration. This gt, this collection of gt is of t inside T inside tau, this curly T is a filtration. You can check that it's by construction, it satisfies the definition of a filtration. You have these nested properties becoming bigger and bigger. This one has a name. It's called the natural filtration, because it's the most natural one, natural filtration. And you see, I took always the smallest one, which means that any other filtration is bigger. It's contained in, I don't have enough space, contained in any other filtration adapted to xt. It's contained in any other filtration adapted to xt. This is quite natural. There is one more which is natural. For some reasons, for some technical reason, we want to add some points or some very small sets with the property that P of this small set is 0. So we want, sometimes it's useful to add all sets which are of measure 0. So there is one more natural filtration. If we add to this gt in tau all sets B inside, sorry, they belong to F. They belong to F with their measure is 0. This is still a filtration. You can check it still satisfies the filtration. We get it has another name, the augmented natural filtration. You can wonder why we do these kind of technicalities. If you attended the course last semester, you remember when we deal with functions, with L2 functions, sometimes we want to identify some functions. If they are equal almost everywhere, if where they are not equal is negligible. For this reason, we need that this filtration also contains the sets which are of 0 measure. It's a small thing, but in fact, it helps you. It's maybe more complicated, but it allows you to consider equivalence class of object. And I'm going to give you two notions of equivalence, and one is quite nice. And you will tell me why. Do you have any question? So we started stochastic process. In the definition, a filtration was given, but as I said, many authors do not speak about the filtration from the beginning. What it means they construct the natural filtration by taking the preimage of all the set in lambda. And if necessary, they add the sets which are called the negligible sets. These sets with 0 measure are called negligible. And even I should not use the word sets. I should, if I want to be precise, I should say negligible events, because the subset are called events. So this is even more precise. Yeah.
Sigma algebra and sigma subalgebra?
Sub means it's smaller. So if you start with as I said, a sigma algebra is just a collection of sets which is stable on the complement union and intersection. If you take a subset having the same three properties, it's a sigma subalgebra. So it's also a sigma algebra, but compared to the big one, it's a subalgebra. So it's always if you compare it with something else. Yeah, like a space on a subspace is a space in itself, but if you consider it in something bigger, R2 is inside R3. But if you just live in R2, then you are living in the space R2. Maybe we live in dimension 25. I don't know. About equivalence. I just want to, I told you, it's slightly technical, but I find it interesting. I am going to compare two stochastic processes. So I need to write the collection FT. And a second one with the same ingredient, the same filtration, but another collection of random variables. The only difference is about xt and yt. We say these two are, they are called either versions or modifications. These two words are very precise, but you can think about equivalence in a certain sense. They are called versions or modification of each other. If what is the thing, if for any t in this set of time, the probability that I will explain. So what does it mean? You look at the omega, and remember xt and yt are function on the set capital omega, so I can evaluate them at one point. And if you look at the set of points where they are not equal, if this is of measure 0, so very small, then you say that they are versions or modifications of each other. This is a kind of, you don't really see the difference because the difference is of measure 0. If you measure something, you don't see the difference. You don't measure the difference. Okay, this is a definition, that's it. But you cannot, if you think about it, you cannot make this definition precise if you don't have the negligible sets. And now a slightly different version of equivalence. These two things, I like it. They are okay, I don't know how to pronounce this, indistinguishable. You cannot distinguish them if the probability of the set of omega please look at these two definitions. You should see something. Are they equivalent or are they different? Here, t is fixed. For each team, we check something. There it is, you take any team, and you take the omega such that there exists a t such that this is different. So probably you have much more, or you have many more omega here, because you have to look at all times. So you could say, oh, but the union of a countable union of a set of 0 measure, what is a measure of the countable union of a set of sets of 0 measure, is still 0. So why there is this second definition?
a larger, maybe even the T value, you can have a bigger.
Yes, there is no difference in between these two notions if T is discrete. No, so it's a remark. No difference if this set curly T is countable, because a countable union of sets of zero measure is still of zero measure. But there is a difference, if tau is either R, tau is not tau, this curly T is a R plus or an interval, because you have an uncountable union. And an uncountable union of set of zero measure is not always of zero measure. So be careful about this. For discrete time, these two notions are the same, so it's boring, it's not interesting to make a difference. For continuous time, a continuous union of set of zero measure can be of full measure or can be of any measure. It's not always of measure zero. Okay, I just wanted to stress this. It's a nice, yeah, I'm sure you can, if you're interested in this small subtlety, you can explicitly construct a continuous family of set of zero measure and end up with a set of measure one, or of measure which is not zero. So this is a nice thing. Now, we discuss about the filtrations. I did not speak so much about continuity. I need to have some regularity between T and the next one, T and T plus epsilon for very small epsilon. I don't want to have such a big change. I don't want to have a function which is arbitrary at every point. So I need a notion of continuity. So about regularity. This was about equivalence, now about regularity. There is one notion which is not good. One possible, but it's not the correct one. One possible requirement. And you will see why it's not so good. Is that, let me write it. I could say that this function of two variables, one variable is a time, the other one is element of capital omega, going to this set capital lambda is measurable. Now I need to be a little bit more precise from which space to which space. From the measurable space tau times omega. With the sigma algebra, we have already seen when you do a product, like a Cartesian product, you generate the sigma algebra by taking the elements of this variable and the element of this one. Here we are just on a subset of R, or discrete set. This is a sigma algebra. I didn't discuss, but I mentioned it. This is the usual sigma algebra generated by open sets on R. So if you think about R, you have the open sets, you generate a sigma algebra. If it is discrete, you take the intersection with your discrete set. This is just the countable, the power set if it is discrete. So this, maybe this is a Borel algebra on R, or R plus, I'm dealing with, times F. So this is one measurable space going to measure to this one. So this could be one possible requirement. It's measurable from this space. It's well defined. We know everything. However, what is missing in this definition is this notion of filtration. There is no condition about the filtration. It's only this F. So it's not so good. It's too, I think it's not too strong. It's too weak, in fact. Yes, so you, I can put a parenthesis here, yes. This is what you mean. Yeah. You take, I mean, if you have just R plus, you forget this. If you take this, I just want to have a notation both for the discrete case and the continuous case. So that's why I take this intersection. So as I said, this is in fact too weak, not too strong, too weak because it doesn't take care of the filtration. As we have seen, this FT measurability is stronger than the one without FT. So what is the correct definition? And it's fun. In order not to write always a stochastic process with these 5 sets, I just call it X. The stochastic process. In the note, it's a curly or black X. Is progressively measurable. We will forget this definition in a second because the next one is going to be stronger, but it's a quite natural one. That's why I decided to give it. If for any t inside this curly set of time, the map, I still want to have, I change the name, S omega goes to XS of omega. This is not different, but what is different is here. I want to have tau or curly t inter 0t. This is the parentheses. So I just care about the time up to time t times ft. No, sorry. No, sorry, this is meaning. No, yeah, I'm doing a mistake. It's still omega. Yeah. No, now this is correct. Ah, sorry. Yes, there is an inside. This pair is inside. Omega is still inside capital omega. S is inside only this interval up to time t. This map is measurable. But now I'm going to change from. So look, I need to take something more precise here. And I can take something more precise here because now it's for a given time, t. So from this space, it's a little bit long, but curly t inter 0t times omega. But the sets I consider are sigma of the Borel sets on the real line, but only restricted to this interval 0t. So you just look at a smaller set, but times ft from this space to omega. So I know it's technical, and as I said, we are going to forget this in a second, but the point is it's very nice because you just look from time 0 to t. For each fixed t, you use only the minimal information available. Time is only from 0 to this t. And the sigma algebra you consider is not the biggest one because essentially you don't know the future. This one contains already the information about the future. As I said last week, ft is essentially, it contains the information up to time t. So you use this information up to time t, ft. So and this term progressively measurable is correct one, because at any time you only use information available up to this time, not about the future. Okay, this is slightly technical, but now, as I said, there is a stronger condition, not stronger condition, but a stronger definition. Measurability is something very weak. We prefer, and you certainly prefer, continuity. Continuity is something you're familiar with. And most of the process we consider are continuous. And if it is continuous, automatically it satisfies this. So I need to give the definition of continuity, and then you will say, oh, but we have a problem. So I let you guess what is the problem in this definition. I keep capital X with xt from omega to lambda is continuous if any omega belonging to this set, the map Okay, what is the problem with this definition? Giulio, can you see what is the problem? Wait, can you answer? No, there is no problem of measurability. It's worse than this. Another.
What's the policy?
Yes, what means continuity? It's more basic than this. What means continuity in this general setting? I didn't define it. There is a notion of topology. I don't want to go in this direction. Last semester, I mentioned topology. So I'm going to add one keyword, which saves us. I'm going to write standard. I hope you remember what I mean by, it's not it's just for this course that I'm going to call it standard. But standard means this lambda is either R or Rn or set of matrices where you have the distance. You're familiar with this. Sorry. So you have this notion of norm which defines the topology. So if you think about R or if you think about Rn, you have the usual definition of continuity. Otherwise, I need to define continuity in a certain sense, and I don't want. So I'm going to, in fact, in the applications, the only thing we measure is something in R, something in Rn, maybe in matrices, but not more than this. So it's continuous in the sense you know from calculus 1 or calculus 2. That's it. That's enough. So I need to assume that lambda is standard just to give a meaning to continuous. Otherwise, I need to say more about this set. And the measurable sets on topological space are not, yeah, they can be different. The two things can be different. So you need probably a metric, then you can define both. So I don't want to speak about this. I think it's complicated enough. Let's be simple. Let's be simple. This is continuous. Sometimes it's too strong because, look, I'm asking this for all omega. All omega, that's too much. So it is almost surely, I already mentioned this AS last week, almost surely continuous if the set of omega inside omega such that this t goes to, I make it slightly faster. This continues. If this set, if we take its weight, it is of weight 1. So for almost all omega, it's continuous. Maybe it's not continuous on a set of measures 0. So the probability, the measure of the set of omega such that this map is continuous is of norm 1 or probability 1. If there is a few points where it's not continuous, you don't care. Yes?
I have a question about the measurability. So there are two sets. One is the set that you mentioned earlier, which is there exists some t such that xt is not equal to yt for some omega.
Yeah.
And also we have this set. So can we say that these sets are measurable?
I take it in the definition. In the definition of the stochastic process.
Yeah, but after take some t then have the measurability. So I guess we need this regularity about the you write at the
Which regularity?
the left-hand side.
You need it as a basic thing, and then you ask more.
If they fix some t and we just have measurability for every t, then I suspect that we cannot say that.
Okay, I need to think more carefully. I cannot answer. Yeah, it's quite technical. Okay, we can discuss, but this is really technical. If you look in books, it's a nightmare. The point is, this definition is understandable. Measurability is indeed much more tricky. And since I'm building this course from different books, I try to check that all assumptions are taken, but yeah, I can do mistakes. The point is, this continuity I mentioned is stronger. This is a theorem, it's not easy. So continuity, in the sense I mentioned, implies progressive measurability. But this is a theorem, it's not straightforward. And again, if you look at books, some books have 20 or 30 pages just on this topic. So yeah, it's rather tricky what kind of information you put on the different object. But yes, if you think there is a small mistake, I'm ready to look at it. For us, and for the Brownian motion, we will have for free the continuity, which means we have that directly this measurability and so on. Okay, there is one more thing that I just want to mention, because we look at some regularity of this map, t goes to xt of omega. There is one object where we haven't defined any regularity. It's the filtration itself. I said it's a family of subalgebra, blah, 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 and they include each other. We can also have some regularity between this inclusion. So regularity. And then this is the end of this technical part on filtration. And this, if you look carefully, it also plays a role. So I set f, it's a notation which is quite common, f t plus, or sometimes it's called f t plus 0. It is the intersection of all ft plus epsilon for epsilon bigger than 0. So remember, ft is a collection of subset having some conditions, and you take the intersection. It is a sigma algebra. It satisfies a condition by construction. So we say the filtration, its definition, the filtration is right continuous. In calculus 1, I try to avoid left and right continuity. I just take about continuity, but here we make a difference between left and right. It's right continuous if ft is ft plus or t plus 0. It means if you come from the future, and you go back up to time t, you have an equality. Say it's right continuous. And I will just give you a picture for what it means. It means very roughly that the information available right after t is known. It's very imprecise, but just to give you a feeling, it's known at time t. And if you want to have a picture, of course, it's a very rough picture. I'm not sure it's really meaningful, but think about, I take this axis as time, and I call this t. Suppose you have a continuous function up to time t. At exactly time t, you cannot define the derivative. The usual derivative, because the usual derivative means you should know it already at a point here, which you don't know. Nevertheless, if you know that the function is continuous, you can compute the left derivative. So it's the derivative, but only considering difference on the left. And if you know that you have this property, you can already say, oh, the derivative will be able to compute in the future. I already know it. This is the best picture I have for this notion. But of course, if your it's a very strong requirement because, and probably it's not even correct, because if your function is still continuous, but is not differentiable, you cannot guess the future. So this continuity has to be understood on this picture more like differentiability. If you know that the function is differentiable, the derivative computed from the left is going to be the same than the derivative from the right, even if you cannot do it. If it is only continuous and you have not a derivative, then you cannot. This is the best picture I could think about.
I think that actually by definition of filtration, it will be left continuous.
No, it's not always the case.
From the left?
From the, sorry. Yeah, by definition from the left, it's okay. Yeah, but you need to say something from the right. It's an additional condition. Yes. Okay. If you want to keep this in mind, it's probably good just to have something. So we say that it's right continuous if it has this property. In the notes, I've wrote a little bit more about this notion, but for now it's enough. I want to go to Brownian motion. So I know it was technical. Please try to check that what I introduced is meaningful, and indeed, I just studied the different objects we have in the definition of a stochastic process. Any question or remark? You haven't written any report yet. No, I don't know. Quite often people study only stochastic process which are right continuous, or maybe I can say it standard. I see I wrote it in the notes somewhere, but let me just, okay, I don't know if I put it in my own note, but standard, it's written in the note more precisely, but standard stochastic process. So this means right continuous filtration. So it's important, right continuous filtration. Plus negligible set included. So it means most of the time and for most of the theory, you assume these two conditions because these are it's a nice framework. I think it's written in the notes. And whenever, if you open a book and the person is not speaking about filtration, it just defines a Brownian motion. I will make a remark about this. Without mentioning filtration, it means this person is considering the natural filtration, which I have introduced. It's considering the augmented one, so it adds a negligible set. So it means you do this. And in fact, for Brownian motion, you can show that it is right continuous, so you are directly in this framework. So if nothing is written, you are in this framework. That's why, depending on the book, if they are very precise, they speak about filtrations. If they are not so precise, they just don't, at least at the beginning, they don't mention it, like I did when I introduced Brownian motion last week. And we will come back to it, but because it's implicitly given by the construction. 2.4, Brownian motion. So it's going to be a stochastic process with value. You can define it in Rn or in R. And it turns out that we are going to start with R because indeed the version in Rn decompose into n independent Brownian motion in one dimension. I check it. So it means even if we study it in one dimension, the n-dimensional case is just n independent copies for each variable. So it's not a big limitation. And I ask you to check some picture about Brownian motion because I cannot do so much. You have probably, or do so many, you have probably see these kind of things. Yes, this is a one-dimensional Brownian motion. It's one-dimensional because, and this is something I wanted to mention, on this axis you have the time, and the one dimension is here. And I'm going to give the definition, but it means you measure a position at any given time or at fixed interval of time. If you have a two-dimensional Brownian motion, it would more look, it's more messy because you don't represent the time explicitly, it's a parameter. And in 3 dimensions, it's a cover of this course. You can see a picture in 3 dimensions. But the one here is 1 dimension. I wanted to emphasize. This is a 0.0. In fact, even I shouldn't say this is a Brownian motion. This is a realization. It's called a realization. Why? Because if you observe something which indeed has a Brownian motion, and if somebody else observes it later or on a different setting, you will not observe the same thing. What you will observe, in fact, is even completely different. Somebody else at the same time, but maybe in a different room, will observe something like this, and there is nothing. You cannot compare them directly. Nevertheless, their properties, and this is something I'm going to explain, their properties are the same, but they are different realization of the same process. So you have maybe seen on internet, there are some pictures with several curves, and they are all going in different directions. They are all realization of the same process, but yeah, whenever you do the experiment or whenever you measure something, you're going to measure something different. So it's very different, and it's the same when you play with a coin. It's never the same thing that you're going to obtain the same trajectory. Please keep this picture in mind. And instead, just before I give the definition, we use, and it's a common use, we use a notation B of t for t in R plus instead of x. Of course, B for Brownian. This is quite common. And B of t is going to represent the position at time t. But be careful, it's a random variable. So it doesn't mean your system is going to be exactly at one position. It's going to be a probability to have your system at a given place. So B of t represents the position at time t. And what about the difference bt minus bs for t bigger than s? This is going, okay, I just do it again. At 2 consecutive time, this is a difference of position. So it's called either the difference of position, change of position, or the increment. This difference is it's either the difference of position, between time s and time t, or increment. Okay. So what is the definition? Of course, again, it depends on the book. You will see different definition because you can use some properties as a definition. I will mention it. So I take in a sense, the most general one. I take it on R plus. You can also define it on an interval. But if you define it on an interval, you can just extend this interval. And as I said, I call it BT. So this is a stochastic process. Is Brownian motion. I should still say one thing. It's one-dimensional. So with BT from omega to R. And in particular, we are in the standard framework I mentioned before about continuity. So with BT in R, this is a Brownian motion. If at time 0, this is a kind of normalization, you are almost surely at the position 0. This is why I put the 0 there. This is our starting point. This is right?
So you're almost surely or
in the book, they write like this. But this is defined only up to a set of measure 0. So it doesn't change. For any 0 smaller or equal to t, smaller or equal to s and then t, s and then t, the difference bt minus bs is independent of fs, and you should complain because this is something I didn't mention so far. A random variable independent of sigma algebra. So I have to explain what it means, and I will do it right after. And the third condition is for any 0 smaller or equal to ts, t, bt minus bs. N 0. All right. So this is a Brownian motion, only 3 conditions. The first one, as I said, you can think about it as initial condition. You just say where you are at time. where you are at time 0. The second one, I will explain more precisely, but how you should think about it, and I will write it, is that the increment between time s and time t is independent of the past. So no matter, well, the picture is no more here, but no matter how you get to the point s, what happens after s, or the increment, exactly the increment between t and s, is independent of what happened before. And the third one is, it tells you that this random variable follows a Gaussian of centered at 0 and with a variance, it's a one-dimensional, so this is variance t minus s. So it's spread with like t minus s. Okay, this is a definition. What the missing part, or what we don't understand yet, is this bt minus bs independent of fs. What is the meaning of this? I already said how we should interpret it. It means what happens after the position or the increment after time s is independent of what happened up to time s. So comment about the second one. So we already know, we know the independence of two random variables, of x1 and x2. We have seen the definition of independence of two random variables. It means a joint measure is a product measure. Okay, so we know it. I take it for granted. Now what means F1, F2, these are, curly F is always for sigma algebra. What means that these two sigma algebra are independent. I didn't say it so far, sorry. So I need to give you a definition. If this is a definition, so I can write a if and only if. Remember, these are made of subset.
Because if it's equal to 0, then right?
Which one?
0, s is less than or greater than equal to 0.
I guess I can take both. It doesn't really matter. There it's important. Or yes, in my notes here, oh, you're right. In mine, no, I put, okay, I don't know. Check, exercise for you. Check if there is no contradiction putting it equal. I don't think there is a contradiction. In the notes, what did I?
You're right. Exactly.
Okay, so probably it's fine, but you can check. Okay, what means two sigma algebra? Two sigma subalgebra of F are independent if whenever you take an element in F1 or any A2 in F2, then the probability of A1 intersection A2 is a product P1, P of A1 intersection with P of A2.
I think it should be multiplication.
Yes, it's a multiplication. Yeah, you're right. These are just numbers. This is quite standard for the independence of two sets. So it says, no matter which set you take in F1, no matter which set you take in F2, it respects this. If you think about, if you want an example, your height and the color of your hair, these are two, it should be independent. So F1 is related to the color of your hair. F2 is your height. If you measure both, most probably they are independent. This is yeah, so you can do stochastic process like this. No question. It's just an example. Okay, now, so we have two notions of independence for random variable, for sigma subalgebra. Now this is something mixed. It's a mixture. Remark, and this is an exercise for somebody. Anybody? X1, X2 are independent in the sense already mentioned in section 1.3, if and only if sigma of X1, sigma of X2, the smallest C star, no, not C star, sorry, the smallest sigma, the smallest sigma subalgebra generated by X1 or the smallest sigma algebra generated by X2 are independent. If you want to play with definition, it's a 2 lines before, but you need to think about the definition. These two things are equivalent. Okay. Still, here this is something, it's a mixture because I'm saying a random variable independent of a sigma algebra, so you can guess now the meaning. Then, still in this comment, then X is independent of, let's say, G inside F, one sigma algebra inside F, if who can provide a definition? Just compare what is on the left or on the right.
Sorry, smallest filtration.
No, no filtration. There is no filtration here. But indeed, if sigma of X, the smallest sigma algebra generated by X, this is a sigma algebra, is independent of G. Because now we have two sigma algebra, so we have a definition of what means independent. Okay, so it was just a comment to give a meaning to 2. This is a random variable, so you can look at the pre-image, because it's a random variable, it has a smallest sigma algebra, and you can look at its this smallest sigma algebra, and it has to be independent of this one. And again, the interpretation of 2 means, again, this is, the condition 2 means the increment, because the difference is an increment. The increment is independent of the history up to time S. Okay, I gave you one definition for the Brownian motion. Start at 0. The increment between time t and time s is independent of the history, and this random variable has a specific distribution. And again, if this is becoming bigger, this variance is becoming bigger. So it has a bigger spread. And indeed, if you look at many pictures about Brownian motion, you will see that, again, on this picture I made before with the time, the spread or how it's distributed is growing over time. And I think it's growing like the square root because this is a covariance, but it's a sigma square in the general definition, and the spread on the paper is related to sigma, not sigma square. Okay. Remark. And now we are lucky because somebody worked a lot for us. With this definition, BT for any t in R plus can be modified. And I gave a definition of a modification. So I'm exactly in this setting, can be modified to a continuous stochastic process. Which means Remember, this modification is for every time up to a set of measures 0, you can consider that your Brownian motion are continuous. So it's not in the definition, but since you can play a little bit and get a continuous one, of course, we are going always to choose, we always choose a continuous version of the stochastic process, of the Brownian motion. And again, I have a picture more related with L infinity of R. So for those who were here last semester, you remember we have functions which are bounded, but they can be unbounded up to a set of measures 0. You can, the point where they are unbounded is of measure 0. So what it means, if I don't want to have such a nasty function, I just change the value. So I forget these points, which are of value of measure 0, and I decide to take the function which I cannot distinguish them because the only difference is of a set of measure 0. I choose the one which is bounded and not only essentially bounded. This is essentially the same thing here. We have a few nasty points or nasty paths. Here, a point is a set of omega, capital omega. We have a few where it may not be continuous. We just forget them and take where it's bounded and not only essentially bounded. So it's again, I forget something which is of measure 0. And somebody, it's a deep theorem of Kolmogorov, tells me that I can do this. I can forget the points where it's not continuous, and this is of what I'm forgetting is of measure 0. I told you it's a tricky theory. I'm trying to give you the main ideas, but there are plenty of deep results behind this.
Last time where we did the smoothing, where we made a very something so more continuous one by requiring that the difference between those two are of measure less than epsilon. Is it the same guy?
Okay, I don't see what you have in mind. Tell me at the end. Okay. Some properties of the Brownian motion. So from now on, whenever I say Brownian motion, I assume this continuity. And on the picture, on all the pictures you can see, they take the continuous version because the point where it's not continuous are almost invisible. What is a Brownian motion? It's a proposition. And we will understand a little bit more with this. So omega f, I'm thinking about having one comment for writing all this instead of copying each time. Okay, just a stamp, you write all together. Okay, I forget maybe in the previous definition, I said in the previous definition that it's from omega to R and not RD. So it was a one-dimensional Brownian motion. I did not mention 1D. So in the definition I gave for Brownian motion, please say it's a 1D Brownian motion, because I assume that we are having image in 1D and it appears in the definition, it appears here. This is one-dimensional. Yeah, I will mention the n-dimensional case at the end. But so in the definition, please write 1D Brownian motion. This 1D is important. Yeah, I wrote it in the note, but I don't think I did it on the blackboard. So blah, blah, blah. is so let be a 1D Brownian motion. Then I'm going to state three properties. The first one is stupid because I just copy B0 is 0. But you will see why I just copied. Of course, we know it because it is in the definition. For any 0, so I call it T1, T2. Whenever you choose n time, the vector B, which is B at T1, B at T2, to B at Tn transpose, it's a random vector, is a Gaussian vector. It's a Gaussian process, or Gaussian vector, or Gaussian process. It's a Gaussian vector with expectation of B is equal to 0. This is a vector 0. Be careful in Rn. I will comment on this later, but it means if you pick n times and construct this random vector, this is a Gaussian vector in the sense I introduced last week. So it means the Brownian motion is a Gaussian process. If you look at the definition of a Gaussian process, so let me already stress this, this condition means dt T in R plus is a Gaussian process. And the set of Gaussian process is inside the set of stochastic process. And the third thing is expectation of BT BS. So expectation of this product is, I use sometimes this notation, but this is just the minimum between T and S. So this is a property that it's not even difficult. This one is not difficult, and probably both are not difficult. So if somebody is interested, and I can give you some references, how we deduce from the original definition these properties, that you have a Gaussian vector for any n time, so it means you have a Gaussian process, and that this property holds. But this is not the end of the proposition. And properties 1 to 3, they define a Brownian motion. This cannot be true. Why it cannot be true? I need to add something. It cannot be true because in the definition of a Brownian motion, we have a filtration, which is a starting point. So it means it's a Brownian motion with the augmented. Let me do it like this. And now you should feel relief. You should feel happy. Why? Remember what is the meaning of this? It means whenever we have a family of random variable, one random variable, we can define the smallest sigma algebra, and then we can define the smallest sigma, the smallest filtration. And if I add the set of measures 0, we have what is called the augmented. Why you should feel happy? Because remember last week I mentioned Brownian motion only with this information and this information. And I said, oh, this is a Brownian motion. And indeed, it's very limited. These two information is very limited. But this result tells you, oh, this is enough in order to construct a Brownian motion with a real definition where you have a filtration if you consider a special filtration. So in some books, they don't speak at all about filtration. They just say a Gaussian process, a Brownian process is a family of random variables satisfying, satisfying this with this understanding and this, but indeed it's sufficient. But what you lose, you get only the one with one filtration. While this is sometimes interesting to have a more complicated setting. So you get only the simplest one, I would say. Why simplest one? Because remember, this filtration has to contain at least the natural filtration. Otherwise, it wouldn't be adapted. But still, you can have more information here. So you have, in fact, in this one, you get the minimal information. But still, it completely defines one Brownian motion. And I can even say this one, okay, this one, it's a parenthesis, is right continuous. Remember, right continuous means the filtration has this property that when you go back from the right, you obtain FT. So this filtration has this property. So it means, if you remember, I made a remark, whenever you have augmented, which means the negligible sets are included on right continuity, it means these two things mean we are in a standard stochastic process. This is just a small thing. All right. Okay. I still have a few minutes, so I'm going to give you one more result, which is nice. I mentioned it. Do you have any questions first? No, it's dense. I'm not expecting you to understand 100%. I don't understand 100%. I was surprised. There are entire books just on Brownian motion. So it means you can really study many refined things. We are not going to do it. Let's have just a partial understanding, but it's better partial than zero. Hope so. Okay, a few more properties because it's nice. They are nice. So properties under transformation. Properties of transformation. No, under transformation, it's better. Under some transformation. So let me just call this X. I don't want to copy it. So I call this capital X. Let capital X be a 1D Brownian motion. Then, so there are these three nice properties. The first one is this: for any S bigger than 0, omega F. Sorry, I copy the last thing below here. I consider the same thing, but with a shift. Oh, no, sorry, there is a mistake. It's not correct. This is this minus BS. S is fixed, so think about function of t, that you have a shift. This is a 1D Brownian motion. So it means this is a shift in time. When you start with a Brownian motion and shift it in time, so you start at time 25, then what you observe is again a Brownian motion. So it's a kind of independence with respect to your starting point in time. And indeed, if you look at these kind of pictures, and now you forget, okay, now you forget what is before, you will just see a new Brownian motion. There is no difference, except, yeah, even this shift is important just to start again at 0. I mean, if 0 was here, of course, now I need to put the 0 here. But this is a shift in time. The second property is, again, omega ft, the same filtration ft t in R plus. But now I look at minus bt t in R plus. So what I do, you change your point of view, you put your head below, you do a mirror, there's a minus sign, you get again a Brownian motion. So exchanging or flipping up and down, you get again a Brownian motion. Is 1D Brownian motion. This is a mirror reflection. Mirror reflection. There is one more, which I mentioned at the very beginning in the motivation about the change yen and dollars. For any c bigger than 0, the following thing. Now I change the filtration. I rescale. This is going to be a rescaling. I divide by c squared. C is a positive number, strictly positive number. And I look at c times b t over c squared. Is a 1D Brownian motion. What does it mean? And I mentioned this at the very beginning of this course. If you have such a picture, okay, and now you zoom on this part with this factor. So you dilate time with the coefficient c squared, and you look at your motion with a coefficient c. So be careful, it's not the same scaling. You do not the same scaling in time and in space. But if you do it like this, and you just look at this part, you are going to see again a Brownian motion. So no matter how much you zoom inside, you see the same picture.
If you don't scale it by c, and instead
then, you mean if you don't do it, probably you will either get something too flat or too, you know, when you do a rescaling, you know, you are just deformed. Like if you take a real picture, if you take your face and do the deformation in one direction, you will not recognize anything. So you have to do it with this, this precise ratio in order to get the Brownian motion with the definition I gave. Otherwise, you get either something too flat or maybe too steep. I don't know. And the fourth one, and I will stop here. I'm not sure I fully understand it yet, but because it's written, I need to say it. Maybe it will play a role later. If I define a new random variable like this, so I take b of 1 over t, and I multiply by t. Of course, I need to say what happens at 0. So I just say z0 is 0 random variable. So this is for t bigger than 0. So it's a kind of, I should have written rescaling for the previous one. The previous one was a rescaling. This is also a kind of rescaling, but slightly different, or maybe inverse of time. This is also 1D Brownian motion. But as you can observe, I'm not specifying the filtration. So it turned out that it's a 1D Brownian motion with the natural filtration. So it means you have to do define the filtration by looking at the pre-image. But still, I like this. This one, I still don't understand what is the real meaning. If somebody wants to look at this, probably you can find some explanation what is the real meaning. But the other three, I think it's understandable. Shift in time, mirror reflections, and rescaling. There is one which I could not fully understand, is if you go backward, but I don't understand. If needed, we will come back to it. But there is also a notion when we come back in time, but I was not confident. Okay, that's all for today. Just let me tell you what we are going to see next week, because it's fun. If you look again at this picture, okay, and if you give a notion to what is the length of this for any interval of time, I will explain this more precisely. In fact, this length is infinite. If you were able to look very, very closely, you would see that the length of this in a precise sense is infinite. And the second property we are going to state is that it's continuous. We know it from Kolmogorov theorem. It's nowhere differentiable. So if you try to give a derivative, nowhere you can do it. So these are two additional properties of the Brownian motion. So next week, we will just finish this Brownian motion, and then we move to a slightly different topic. I know it's dense. Please try to accumulate your knowledge. Thank you. And you can always send me questions, of course.